muted the whole time. Oh, what an idiot. Thank you, Harvey. Sorry, sound is now on. Thank you for those people who are pointing it out. I've been very, very foolish. Let's start again. That's 5 minutes of talking without sound. I do apologise. Okay, thanks, Curtis. Okay. Beginner's mistakes. Let's go back. What I was trying to say was, in differentiation, we have the change in x and the change in y, and what's going on is gradient of a line is how steep it is. So we've got the change in y is how much the output is changing. Change in x is how much the input is changing, and it's how much it goes up by how much it's going to go along. For every 4 increase, how much is it changing its output? And the reason I've got this diagram here is because the point at which it changes is this point here, where it was being an upward gradient, it's now a downward gradient. So at this point here, it must be 0. And I was talking about, well, where does this differentiation come about from? Well, we can talk about rise over run, but I prefer change in y over change in x, because not only is that fundamentally what it is, but if we go forwards, I can look at a specific question. So I'm going to talk about this question here, y equals ax to the power 4, where a can be anything we want. I cannot believe I've just been talking for 5 minutes without anyone being able to hear me. What an idiot. Thanks for pointing it out, guys. Right. If I look at this equation here, I hope you can see that if I'm interested in the gradient of this, I want the change in y over the change in x. That is going to be very important when I consider what's going to go on. Now, it's going to be quite steep, but between any 2 points, I could put in an x value and it will give me a y value. If I increase that by a gap of h, I can put in a y value here and it'll increase as to be the function of x plus h. And that we'll call x plus h. So in the x thing, it's changing by h. If you want, it's x plus h. So therefore, the h is the change. What we care about is this change here then. The change in the function. And the function, if we put in x, we get ax to the power 4. If we put in x plus h, we get a x plus h to the power of 4. So that's the change in y. It's the function when we put x plus h in, take away the function we just put x in. To be able to simplify this, I'm going to need to be able to expand x plus h to the power 4. Unfortunately, we have something called the binomial expansion. The binomial expansion is obviously not for the topic we're doing at the moment, but it does teach us that 1, 4, 6, 4, 1 are the coefficient multipliers to x to the power 4, x to the power 3, x to the power 2, x and 1, and 1, sorry, at this end, and then we have 1 h squared, h cubed, and h to the power 4, giving us x to the power 4. Now, because we're dealing with a, we're going to be adding something else, but we've got 4x cubed h plus 6x squared h squared plus 4x h cubed. So I'm just going to check the chat to see if everyone who is with me is understanding what I'm doing. No one suggested otherwise, so I'm hoping that is making sense. Now, I have set up here that this is going to therefore equal a times that. So we've got a times x to the power 4 plus 4x to the power 3h plus 6x squared h squared plus 4x h cubed plus h to the power 4 all over h. It'd be quite handy here, because it divides by h, if we took h out of everything. And this is going to be possible, because if I carry this on to here, I get a x to the power, I'm going to expand out the bracket, a x to the power 4 plus 4a x cubed h plus 6a x squared h squared plus 4a x h cubed plus a h to the power 4. But we've got to still take away ax to the power 4. So let's do that there and there, because they're both in there. This now means I can actually factorise to give me h out the front and 4a x cubed plus 6a x squared h plus 4ax h squared plus ah cubed. Now the reason this is useful is because this can all divide by this h here. Now I'm appreciating this can start to get messy, so I'm going to delete this bit of working here, and you can always rewind to see what that bit of working was. They will cancel, that h cancels with that h, and because this is a gap, to find the gradient at any given point, we can shrink that h smaller and smaller and smaller until such time as it's practically 0. It's not 0, but it might as well be because it's so tiny. When we do that, that makes that term 0, it makes that term 0, and it makes that term 0. So it's just leaving 4a x cubed. Now that, if we then focus on what our original y was, is y, the change in y over the change in x is multiplied by 4, the a does not affect it at all, and drop the power by 1. And I could have done this with anything. I could have done it with n, but I didn't want to use the binomial expansion to n because it would have got more complicated, and without doing a lesson on the binomial expansion, that's why I'm trying to avoid that. Basically, that means that we've got, any time we've got this situation, we've got the ability to multiply by the power, drop the power by 1, and we differentiate. Now there are, in year 13 you move on to things like the chain rule and the product rule and other rules that allow you to differentiate more effectively, more complicated. But this is what it all is underpinned by, and it's this is the thing that I think a lot of people struggle with. It's from first principles. This is first principles, this idea of whatever we're doing, we have to build it up. Now how am I the best to explain that? Here are some first principles. I'd like you to try all 3. All 5, there's not 3 there. I'm going to work on numbers while you're working on first principles. Each of these is built in exactly the same way. If we do a very small line and call it y equals 4x, we can do exactly what I have said. Put an x in, put an x plus h in, and the things I get out are going to be 4x and 4x plus h. Let's have a look at that. So the change in y over the change in x equals, change in y is 4 lots of x plus h minus 4x all over h. This equals 4x plus 4h minus 4x. I have a feeling that might be disappearing off the side, so I'll move it over. I will get to grips with this whole process of doing this at some point. All over h equals, they cancel out, so 4h cancels with h, just leaving us with 4. And that is the proof from first principles, the derivative of 4x is 4. I recommend you pause the video and verify the other 4. You don't need me to show them. They all work in the same way, and until you can do that, there's no point in being able to do anything else unless you can prove why, because this is a skill in itself. Okay, moving on with the differentiation. Hopefully everyone's with me. Not hundreds of viewers, but enough people are possibly put off by the fact that I was silent for 5 minutes. That was likely enough to drive people away, and it's not really about the viewers. This is hopefully going to be available for people afterwards. I might have to turn it into a video rather than a live video and redo some of the things that were in silence, but never mind. These questions here, I'm actually going to focus on the middle one here, number 2. Because this one is straightforward, it's based on everything we've just been doing. We're going to, whenever you're differentiating, you're going to multiply by the power and drop the power by 1. However, whenever we get a question like this, and I'm going to do a different example, something I prefer to do, y equals 5x plus 7 over x. So, I'm going to rewrite that as 5x plus 7x to the minus 1. We must be prepared, if we've got x on the bottom, to rewrite them in one long line. That makes this much easier. Drop the power, multiply by 1, 5. Drop the power by 1, x to the power 0, x to the power 0 is 1, so it's just 5. Drop the power is minus 2, so it's minus 14, x to the minus 2. And then, and only then, do we go 5 minus 14 over x squared. This is obviously not a question. Find the x coordinates of the points where the gradient is 0. This is the gradient, dy dx. Okay, this is still y. This is where I've got the gradient. So finding where it's 0, 0 equals 5 minus 14 over x squared. I'm going to multiply everything by x. Squared, and I get 14 equals 5x squared. So x squared equals 14 over 5. And x equals the square root of that, which is 1.67. Being as we're A-level students, it's plus or minus 1.67. Okay? Because all square numbers have to be the plus or minus version. Okay? I recommend pausing and completing the rest of these questions. Now, I should say at this point, I have stolen these questions from Maths Genie. Not stolen in any more sense that I'm trying to provide questions that are interesting and useful for people to understand, and trying to give you things that you can then take on. They have more questions there. If you were to go to Maths Genie, you can find more on what we're talking about here. Now, for those people who are in Year 11 looking to move on, maybe this has been a first introduction to differentiation, and hopefully you understand what's going on. A key reminder here is, in order to differentiate, you're going to drop the power and multiply. So if I've got anything, ax to the power n, I multiply by that, giving me n ax, and I drop the power. That's how I differentiate. If it's on the bottom, I have to turn it into a negative power, and then that allows me to multiply and drop the power even further. But what about if we've got the chain rule? This is more in Year 13, so Year 12, this is where you're going with that. I'm very much feeling Gryffindor today. Sometimes I'm more of a Slytherin. Okay. We've got, if I've got dy dx equals something, that's all well and good. But what if I've got x equals 3t plus 4 and y equals 4t minus 7? We'll put a squared on it. These are called parametric equations, and x is defined in terms of a value and y is defined in terms of a value. Parameters. I can't differentiate these, but I can do each one on its own. This one can go dx dt. Let's just think what we just learnt. Dx dy is what we were doing. This has just changed to dx over dt. We did dy dx. So we're going to do dx dt by going multiply by 1, drop the power, so it's just 3. And dy dt, multiply by the power, 8, drop the power from 2 to 1, and the number disappears. The number will always disappear. The chain rule states dy dx is equal to dy dt times by dt dx. We don't have dt dx, we have dx dt. So we have to rearrange that one to dt dx. I did so by flipping this upside down. So I have to flip this upside down, but it's a number. Flipping it upside down doesn't do anything unless it's a fraction. So flipping it upside down makes it 3 into 1/3. So what we can say is dy dx must be 8t times 1/3 equals 8 over 3t. We are finding the gradient in terms of this one parameter t. And if we then knew t equals 5, in which case dy dx equals 8/3 times 5, or 40 over 3, which is going to be able to be simplified. Equally, they might ask where a turning point is. That always occurs when dy dx equals 0. So 8/3 t equals 0 itself. That means I'm going to go behind myself if I'm not careful. So I'm going to go over here. 8 over 3 t equals 0. Therefore, t equals 0. It's the only way it can happen. And so it might ask you when the gradient is 0. That would be the turning point. This has got a turning point when t equals 0. There is a second way we could do this. The second way we do it is we rearrange. I can rearrange this to say that 3t equals 4 minus x, t equals 4 minus x over 3. So then y equals 4 minus x over 3 all squared minus 7. I hope you agree. That seems like a long-winded way of going about it, given that we can just differentiate the parametric equations separately and use this chain rule to help us. So what have I covered today? I've introduced differentiation as being, let me move back to being me. It's quite important that I get the whole of myself on the screen. Hello! No, we've talked about the differentiation being the gradient of any line you want, any function. Because a function and a line graph is just an input and an output. The input goes through some sort of formula, some sort of machine, some sort of operation, and becomes a different output. We can find the gradient of that by differentiating, and we talked about differentiating being in a simple form. If you've got an amount of x with a power, you multiply the coefficient by the power, then drop the power. Later time I will do a lesson on integration. I may redo this or cut out the whole of the silent bit, but hopefully that's been useful. If there is anyone still here in the chat who has any questions, please do say something, because I'm going to call it now because everything's been done and everything's been covered. I just have one more question for people. If you are still here, here's my challenge for tomorrow. Anyone who can, I probably need to bring it up so you can see it. This is my challenge. Can anyone tweet me or visit Facebook and tell me, or send me an email and tell me what you think the differentiation of this is? This is my challenge to you. I want this to be interactive. I want this to be something where people involve themselves and ask questions and help each other out. If you know the differentiation of this, work it out, get back to me. It's deliberately supposed to be more complicated. I want people to be thinking. Now, one thing I want to make very clear, this is 2 over 7x squared. It is not 2 over 7x squared. Okay? Fractions are not as nice as I'd like them. I might need to invest in a pack. Thank you for joining me. I'm sorry about the silent bit for the first 5 minutes. Beginner's mistake. I will try to make sure that never happens again. Thank you very much. And if there's no more questions, I'm going to head off.